Starting off with just simply what is factorial notation, understanding what it actually is. That is the definition for factorial notation. 0 factorial is defined to be the number 1. From that point, you then what's called roll out the factorials. So n factorial will always be n times n minus 1 factorial. And then you can build all the factorials from there. You roll it out. 1 factorial must be 1 times 0 factorial, so 1 factorial is also 1. 2 factorial would be 2 times 1 factorial, so it is 2. 3 factorial will be 3 times 2 factorial, so it is 6, and so on. So most people just think of it as you're just multiplying all the numbers down. And that definition works until, of course, you get to 0, where the answer is actually 1. It's not 0. 4 factorial, keep going, 24, and so on and so on and so on. So you can always roll out the factorial as far down as you need. That is useful when it comes to cancelling. So if you have something like that, 12 factorial or 9 factorial. Now, I'm not saying you would roll it out completely, you'd probably do it all in one step, but technically this is what you're doing. You're saying, well, that 12 factorial is 12 times 11 factorial, and that 11 factorial is 11 times 10 factorial, and that 10 factorial is 10 times 9 factorial. Oh, the 9 factorials will cancel, and we get 12 times 11 times 10. Now, the reality is we don't put all those steps in, we just know the 9 factorial will cancel, leaving me with 12 times 11 times 10. So when I get something like this, 16 factorial on 10 factorial times 7 factorial, well, it's always the bigger one that I'm going to cancel, because then more of the terms will go. But that 10 factorial will go into the 16 factorial, leaving me with 16 times 15 times 14 times 13 times 12 times 11, because we've rolled it out to the 10 factorial. The 10 factorial cancels. I still have the 7 factorial on the bottom, and now we can just cancel to our heart's content. What one would I have done first? Probably the 7 2s, I reckon. Yeah, there you go. 7 2s are 14, that'll cancel. What else have I got there? Oh, 5 3s are 15. Ooh, 6 4s, 24. Oh, could I do that with the 12 maybe? Yeah, I did. 6 goes into 12 twice, 4 goes into 16 4 times. 4 times 13 times 2 times 11, which ends up being, eventually, there it is, 1,144. Like this, for instance. How do I add these two fractions together? 1 on k factorial with 1 on k minus 2 factorial. I need to get a common denominator. Well, if I roll out the k factorial, I can see that the common denominator has k minus 2 factorial, but times k and k minus 1, which means the top of the fraction is k minus 1. Tidying that up, that's probably as good as I can do. So k squared minus k plus 1 over k factorial, because the k and the k minus 1, we've got cancelling happening there. Yeah, that's the best we end up with. Now, the basic counting principle. This whole idea of permutations and combinations. What we saw with probability is that the basic idea of probability was knowing how many things were in the sample space. What those things were isn't that important. It's the number of things that was important, because then we could work out the probability. So drawing tree diagrams and things like that, fantastic. But once you start talking about large number of things happening, it's very time consuming. And if all I'm interested in is how many objects there are, is there a better way? And that's what we're going to look at. So we start with this basic counting principle. So if you've got an event that can happen m different ways, and then after that you've got another event which can happen n different ways, well then the number of ways the two events can happen together is m times n. Basic idea. So if I've got 3 dice, I'm going to roll 3 dice. There's the question, well, how many ways can they fall? So I don't want to write out the whole sample space, I'm just interested in how many things would be in it. So I go, well, it's got to be 6 times 6 times 6, because that first event, the first dice I'm rolling, there's 6 things that can happen. The second die, there's 6 things that can happen. The third one, there's 6 things that can happen. 6 times 6 times 6. I now know there are 216 things that can happen. I don't have to draw a sample space. So basically this idea then, the number of ways of arranging n distinct objects with replacement, so it means we can get the same thing over and over again, in k different ways would end up being n to the power of k. In the one I just did, it was 6 to the power of 3. Well, how many ways can all 3 dice show the same number? When I do these, I think about what would be happening. Now, if you roll 3 dice, it is no different to just getting one dice, rolling it, rolling another dice, rolling it, and another dice, rolling it. There's no difference to getting all 3 and rolling it once. You've still got 3 dice and coming up with a number. So that's what I say to myself. Well, the first dice I roll, there's obviously going to be 6 numbers that could come up. But I want all 3 to show the same thing. So the next one I roll, there's only one I want it to get, the same as the first one. And same with the third. I want it to show the same thing. So the total number of ways that all 3 can show the same number, 6 times 1 times 1, is 6. This now brings up the logical probability question then. What's the probability that all 3 dice show the same number? Got to be 6 out of 216. We just said there's 216 possibilities all up, and we just worked out that only 6 of them will have 3 of them showing the same number. I don't have to draw a sample space. I can just go bang, there's the answer. 6 on 216, which tallies up to be 1 in 36. So this is the basic counting principle. Here's an HSC one from 1996, quite old now. We got mice, and we're placing them in a maze. This maze has 5 exits. Each mouse is equally likely to leave the maze through any of those 5 exits. But just to make sure we know what that means, they tell us thus: the probability of any given mouse leaving by a particular exit is 1 in 5. They've got 5 to choose from, so 1 in 5 chance. 4 mice. A, B, C and D. They're put in the maze and they behave independently. So what one mouse does not influence what the other mouse does. What's the probability that A, B, C and D all come out the same exit? So how do we use our basic counting principle for this? Well, the total number of possibilities, I'm using that power idea, will be 5 to the power of 4, because each mouse has 5 ways of leaving. So 5 times 5 times 5 times 5, we have 625 different ways they could go out. Now, what's the probability that they go out the same one then? There's 625 different ones. We want the same ones. Okay, it's going to be 5, and here's how I work it out. There's 4 mice in there. So the first mouse goes out any door they like. But I want them all to go out the same door. So it's sort of like that last dice question. Once this first mouse has decided that's the one they're going through, I want the other ones to go through the same one. So all the others go through the same one. So they've only got one choice. So there's 5 all up. So what's the probability? 5 out of 625. 1 out of 125, that simplifies to B. Well, they made it a little bit more interesting. What's the probability that A, B and C go out the same exit, but D goes out a different one? So A, B and C use the same one, D does a different one. So I send D through first. D goes, picks an exit, out it goes. But now A, B and C have to go through a different one. So the next mouse has 4 to go through. It's not going to go through the same one that D went through. So it's only got 4. But then the other 2 have to go through the same one as D. So they've got 1 choice each. We end up with 20 choices all up. The key with doing this is look after your restrictions first. So the restriction here was that D went out a different exit. So that's why I considered D leaving first. So I'll look after that first. So my probability that A, B and C go through the same exit, D goes out a different one, 20 on 625, which simplifies down to be 4 on 125. But they did not stop there. What's the probability that any 3 of the 4 mice go out the same exit and the other goes out a different exit? Well, we just worked out the probability that D uses a different exit. But you remember there was a term that they used in the question, that all the mice were equally likely to leave. So if that's the probability that D uses a different exit, it must be the same for A using a different exit and the others go through the same, which must be the same as B uses a different one and goes through the same, which must be the same as C uses a different exit. and the others go through the same one. So what's the probability that any of the three come out the same and the other goes out a difference? It's those four added together. 4 times 4 on 125. 16 on 125. But they kept going. Well, what's the probability that no more than 2 mice go out the same exit? No more than 2 mice. No more. That's one of those phrases like at least, at most, no more. Complementary event. That's what I'm thinking here. Think about what we've already found. We have already found the probability that they all go through the same exit. We've also just found out that 3 use the same exit. Those 2 things are the complement to what they're now asking. They're saying no more than 2. Well, the complement would be more than 2. And that's what we've already worked out. So we've done the hard work. I just got to take that away from 1 because all the probabilities have to add up to be 1. And so we have our answer, 108 on 125. So that was a really nice HSC question that I asked many years ago now, but great little question. That brings us into this idea of permutations. What is a permutation? That is what a permutation is. It's an ordered set of objects. This is where the arrangement is important. So the order of things happening becomes important. So the first case we're going to look at, we've got n different objects from a set of n. So in other words, we're going to use all the objects. So a little bit of imagination here. Imagine in the corner over here, we have n objects. And I'm going to line them up across the front of this room. Okay? How many ways can I do it? I'm going to use every one of them. Okay? Well, okay, it's basic counting idea. I've got n objects over here. How many could I now pick up and go put in the first place? I've got a choice of n objects. So there are n different ways I could do that. So I've put the first object down. I now go back to the pile. All right, I want to grab one. Oh, there's n minus 1 there now. So I'll pick that up, put them in the pile, n minus 1. Next one. Oh, there's n minus 2 now. And I'm going to keep doing that. I'm going to keep going back to the pile and putting them in line. And I'll keep going and I'll keep going till eventually I've only got one object here. Well, bad luck, but you're going last. You're going on the end of the line. But look what we've created. N times n minus 1 times n minus 2 all the way down to 1. That was n factorial. So it now becomes very easy. How many ways? N factorial. However many objects you got, that factorial. That's how many ways you can arrange them. How many ways could I arrange 5 boys and 4 girls if there are no restrictions? Now the no restrictions question is basically saying what's the total sample space? So if it becomes a probability question, it ends up being the bottom of the fraction. So often it's the first one they ask. No restrictions, how many ways can you do this? Well, if there's no restrictions, it doesn't matter that it's 5 boys and 4 girls. I've got 9 people over here that I've got to put in a line. 9 objects, 9 factorial. Okay? So the gender doesn't matter. And if you're interested in the number, there it is, 362,880. Sort of explains why we make you line up in alphabetical order during an evacuation drill. Imagine if we just said line up however you like, and you've got 30 people in your roll group. How many different ways could you line up? And they've got to mark the roll. So it's logical, they go, do it alphabetical order. But they want the boys and girls to alternate. Okay, we now have some restrictions. And the first restriction is this one. The first restriction is the first person must be a boy. Because if I don't put a boy first, they will not alternate. Because I'll get to the end and I'll have 2 boys left. But I want them to alternate. So I must start with a boy. And there's only one way I can do that, and that is start with a boy. Seems silly writing the number 1 down, but theoretically it's there. But now I know that I have to start with a boy, I go, now I'm going to arrange the boys. Okay, girls, just stay over there for a sec. Guys, go line up. So I'm just arranging 5 people in a line. 5 by factorial ways of doing it. Now I'm just going to go over this pile here and say, girls, I want you to work out the order you're going to in, but when you line up, can you just slot in between the boys? So it doesn't actually matter that they're alternating. All I'm really saying is, well, how many ways can the girls arrange? And then that's it. That's how many ways. So we end up with 2,880 ways of them alternating. So there it is, there's the logical next question. What's the probability that the boys and girls alternate? Well, 2,880 over 360, 2,880 tidies up to be 1 on 126. Imagine if you had to draw the sample space for that question. 362,880. It's just not practical. But then we get this different condition. So forget about alternating. You got the pile over here. The pile, which group of people now? You got the people over here. Go, look, yeah, look, I just want you to go and line up over there, okay? What? You two want to be together? Yeah, all right. Look after the condition first. These two people want to be together. So the first condition is this. Those two girls that want to be together, how many ways can they arrange themselves? Now, it might seem silly to say 2 factorial, but that's what it is. And you think about it, yeah, sure, they can go like that, or they can go like that. There's 2 ways of doing it. But once they've decided which way they're going to be joined, that's it. We now treat them like they're one person. No matter where they line up, they've got to stay in that order. So 2 factorial. It now becomes times 8 factorial because I'm no longer arranging 9 objects. I'm now arranging 8 objects. That group of 2 that have to stick together and the other 7. So 8 objects I'm arranging, 8 factorial. 2 factorial times 8 factorial, there it is, 80,640 ways of doing that. Alright, so that is if I use all of them. What if I don't use all the objects and I only use some of the objects? Going to arrange them, but I'm not going to arrange all of them. I'm going to arrange K of them. The n objects are back in this corner. Okay, gang, some of you are going to miss out, okay? Sorry about that, that's bad news. I want you to go line up. How many ways can I get the first object? Well, that hasn't changed. There's still n that I can pick from. Now I'm going to go get the second object. Still n minus 1, hasn't changed. Get the third object, n minus 2, hasn't changed. But I'm going to keep going and keep going until I get the kth object. So here's the thing. If I'm now grabbing the kth object, how many are there here to choose from? Look at the pattern. When I chose one object, it was n. When I was getting the second object, n minus 1. When I was getting the third object, n minus 2. So therefore, when I'm getting the kth object, it must be n minus k plus 1. But geez, that's a bit complicated. So I'm going to make it look even more complicated. Why do that? Well, the reason I do that is because now I've got that. The top of the fraction just becomes n factorial. The bottom of the fraction just becomes n minus k factorial. Essentially what you are doing is dividing out all the ways you could have arranged the ones you didn't use. So you didn't use n minus k objects. So I'm dividing by the number of ways I could have arranged those n minus k objects. Because it doesn't matter how they're arranged, you're not in the group anymore. So I don't care how you arrange yourselves. That's a lot easier. But you know what makes it even more easier? Thanks to modern technology, there's a button on your calculator. NPK will work that out for you. On a lot of calculators, I think it's either on the multiplication or the division key. You do shift and that one. But again, it's still important you know where it comes from, because sometimes you might not be using numbers, you might be using algebra. Let's do this then. We have the letters of the word problems. Seeing it's our first problem. How many 5-letter words? Now what you have to understand in maths, these sort of questions, when we say the word words, what we really just mean is an arrangement of letters. Nonsense words are words as far as we're concerned. So any 5 letters joined together is a word. How many ways can we do it if there are no restrictions? There it is, 8p5. There are 8 letters that I've got to choose from. I'm only going to use 5 of them. So 8p5. Of the 8, I'm going to arrange 5, which is 6,720. Bang, on the calculator, there it is. Hang on. No. I'm only interested in words that begin with P. Okay, interesting. Look after the restrictions first. So imagine you're writing the word. How many choices have I got for that first letter? Well, I've only got one. It's got to be P. P goes first. There it is. So what is my question now? It's now 7p4, because really it's now no different to saying how many 4-letter words can I create from Roblums? Because P's been used, it's gone. So I'm now creating words from Roblums. 7p4, 840. P is included, but not at the beginning. Oh no, P's had its turn at going first. But M, oh no, we don't like M. No. Can't use the letter M. So alright, look after the restrictions. P is included but not at the beginning. Well, that means there's 4 spots I could put the letter P. It's alright. 4. And M is excluded. Well, that means it's now 6p4, because my question now becomes how many 4-letter words from Robles? Because I've used the P and I'm not allowed to use the M. So I've got Robles left. So 6p4, 1,440. Alright. 6 people are in a boat with 8 seats, 4 spelt incorrectly, on each side. 4 on each side. How did that happen? What's the probability that Bill and Ted are on the left side and Greg's on the right side? What's the probability of that happening? First thing to do, it's a probability question. The bottom of the fraction will be no restrictions. How many ways? So if there's no restrictions, there's 8 seats these people are going to use, but I'm only going to use 6 of them. So 8p6, 20,160. Okay, but we have our restrictions. The first one, Bill and Ted have said, we're going on the left side. There's only 4 seats on the left side. They're going to use up 2 of them. So that's 4p2. Greg comes along. I don't want to sit on their side. He's got 4 to choose from, but only going to use 1 of them. So 4p1. Then the rest of these 6 people, we've got 3 people left, go, I don't know what these people are going on about. We don't care where we sit. There are 5 seats left now, because we've used up 3 of them, and we're going to use 3 of those seats. So 5p3. That's how many ways are left to go. Multiplying that all together, 2,880. Our question was, what is the probability that this happens? So it must be 2,880 on 20,160, 1 in 7. 1 in 7. No tree diagrams, no sample space. Bang, we got the answer. 2006 HSC. Sophia has got 5 coloured blocks. A red one, a blue one, a green one, a yellow one, and a white one. She's going to make stacks of blocks. And there might be a 2 stack, a 3 stack, a 4 stack to form a tower. A tower is not just one block. So we don't have a 1 block. But as soon as we put another block on the other, we have a tower. How many different towers are there that are 3 blocks high? Now, because they're different colours, then the arrangement becomes important. There'll be different towers that they build. So this is why it's a permutation. 5p3. There's 5 blocks I could use. I'm going to use 3 of them. 60 towers. 60 towers. Part 2. How many different towers in total? Well, 2 block towers, there'd be 5p2. 3 block towers, well, we just worked that out. That's 60. 4 block towers, there's 120 different ones we could do. And 5 block towers, there's another 120. So all up, there are 320 different towers that she could make. Enjoy. And if I don't start getting some questions now, there's something wrong. Okay.